All right, welcome to video on applications of the double integral. So in this video, we're just going to look at section 15.4 from our textbook. All right, let's begin with just a summary of things we can do with double integrals. For example, we've already looked at areas. So in this situation, what we've got is we've got a domain D in the plane. So these will go by a couple different names. So let me just draw a little tiny x coordinate axis. So as you remember, I like to draw it like this generically. So this is the domain D, where we think of this as a planar figure. So I'll call this a planar domain. In this section, when it comes to applications, we will say planar domain, but you should be aware of another term that is used in physics called a lamina. A lamina is essentially something that is so thin that you can ignore the third dimension and you can think of it as essentially a planar domain. All right. So if you want to calculate the volume of a region, not volume, area, well, we can use double integrals, of course, and we've got the following formula where the area of the planar domain is just integrate dA. Remember, dA is just a tiny chunk of area. Okay, and if we zoom in again, the whole process of calculus is to cut this up into little tiny chunks of area. And now we've got some options. How do we want to set up our problem? Of course, if it's convenient, you can use rectangular coordinates, dx, dy. Okay, and keep in mind the order, you can pick any order, however, the geometry needs to make sense with respect to setting up the bounds. Of course, we just learned polar coordinates, so this gives us another option. So we've got essentially three options, dx, dy. We can also set this up as dy dx. Again, the limits of integration are going to change. We have to set it up. But we've got also polar coordinates where we have an extra dr here, which could help our integration. All right, so that's one handy application of double integrals. And again, because we have these basically different tools, we have basically new types of areas we can compute using this method. All right, the other thing, which was the motivation for setting up a double integral, was to calculate a volume. Okay, so if I have a volume of S, S is going to now be a solid, where if we use this formula here using a double integral, the expression we say is this is the volume under a graph z equals f of xy, where we're lying above the domain D. So here's the domain D that also is important in this notation. Okay, so what is the picture here? The situation is, well, if I've got a domain D in the xy plane, by now you're comfortable setting it up and visualizing this as in the xy plane, then z is the graph of a function. So let's pretend that this is our graph. I affectionately call this the peanut shell. Okay, and then if we want to have the volume under the surface, we basically have some sort of solid here where you have to basically go under the shell but stop at the xy plane. So together all of this is what we're calling S for the solid. We kind of abuse notation here where sometimes we use S as the surface. Okay, so again, thinking of volume under the surface but above the xy plane is another application of the double integral. So this one we haven't looked at before, but it's very simple and it's a nice generalization of the average value. So for example, if you've got some sort of planar lamina, but they've got different temperatures all over the place, where F is measuring the temperature at every point xy. So in this case, it might be more appropriate to look at this little piece here, right? Where at every point x comma y, you've got some sort of temperature. measured by F? Well, if you want to look at the average temperature over this planar domain or this lamina, you can use the second formula right here. So I like to call it AVF for average value of F. And the idea is the double integral of F times dA is now interpreted as the sum of all of the values of F, essentially, but then you divide by the area of the domain D. Okay, keeping in mind that that's really how the average should look. I mean, if you think about taking average of test scores, you add up all the scores. So adding up all the scores would correspond to summing up F along your region, and then you divide by the total. Okay, so another way I kind of like to think about why this makes sense from a unit perspective, if you've got little tiny chunk of area, that doesn't really make sense for the value of the function, right? We just want summing up F. Well, you've got an area here to kind of cancel out units of area. So in that sense, I feel like, that's very loose, but I think conceptually, using unit analysis, this should convince you that, okay, this does indeed calculate the average value of a function. All right, so pretty simple formula, not much more to say about that. The next topic is to look at density and mass. Here's where all the physics comes in. So for all the engineering majors, this is something to really pay attention to. So you've already seen density and mass, I hope, in Calc 2. So let's look at this again from a slightly different point of view. So just physics notations, let's review what is density. Density, physicists say it's amount of mass per, and I jokingly say per geometry. Why do I say that? Well, because it depends on the context. So if you do units of length, you're imagining maybe perhaps a thin rod where you're only measuring length along a rod. So in that context, yeah, mass of the rod per length. But right now, we could also think of what if we've got a lamina. Okay, then the units would be mass of the lamina divided by a unit of area. And of course, we can also even go into higher dimensions where imagine you've got some sort of solid here. So later I'll call this the walnut, but we're not there yet. Where you've got some sort of solid. Okay, and if you've got mass of a solid per unit of volume, which would make sense again. And a little tiny piece of length, you visualize it as essentially a dx, I suppose, is a little measurement of x here. A little bit of area, think of that as a little dA. And then later we'll think of a little tiny chunk of volume, dV. Okay, the key here is you'll have to talk to your physics professors to more carefully look at this word mass, but intuitively I always think of mass as essentially the collection of molecules, let's say atoms. It's like a physical quantity, whereas density is mass in a certain region of length, area, or volume, depending on the context. All right, a couple of different common notations for that is we are going to use rho in this section. Rho is just another Greek letter. Here, rho is going to depend on x and y, where x and y is just a location along our lamina. But every now and then we might also use delta xy. So of course, delta you've seen before in epsilon delta proofs in Calc 1. So since density starts with D, delta is another common notation for density. Okay, so what we have then is, let's start with mass. Mass is the simplest concept. Again, starting from the physicist definition of density as mass over geometry. In this case, we're going to focus on mass over area. So here's where this language of infinitesimals really starts to shine, because again, we could do this very rigorously using, cutting things up into little chunks, etc. But you've seen that story a few times already. So it's much nicer to just kind of say like, okay, we could do this rigorously, but let's do this intuitively. dm is going to be a little tiny chunk of mass. Okay, I like this notation, right? We've got little bit of mass right here. So what is that? Well, we're going to assume density depends on a pointwise sense. So it's just density rho times a little tiny chunk of area. Okay, again, just that's solving the equation density is mass over area. Solve that for mass, we've got density times area. Okay, since this is just a little tiny bit of mass, well, now we use the machinery of calculus to say, okay, if I want the total mass, all I have to do is just add up all the little tiny chunks of mass. So for me, this is how I actually really like memorizing my formulas. So I'll put a little heart by this one where it's a double integral over the plane, and dm is just add up all the little tiny chunks of mass, and then when you're done, you'll get the total mass. Okay, but if you have a density function, of course, you can just use density times dA, and that's the same formula. All right, that's it. That's all there is to mass. So where it gets more interesting is moments and centers of mass. So the formulas are actually very easy, and I'm actually going to pop over to my notes from Calc 2. So I won't go super detailed here. You can maybe pause the video and read what's on the screen here. But very briefly, how do we find what's called a center of mass? The story begins with a seesaw, and you imagine two masses on basically a weightless beam. And the idea is you see this little triangle down here, which we call the fulcrum, that's like, okay, where do I put that in order to balance the masses? And I always like to think of some simple scenarios here. Like if the two masses are exactly the same, then we basically should put that right down the middle. Okay, that makes sense. If the second mass is twice the first mass, I can think of basically having two stacks of boxes on the right. And the idea is, well, putting the fulcrum in the original halfway point is not going to work anymore because you intuitively know that the two boxes are heavier than the other one. So essentially, it's going to topple over on the right-hand side. So the way to think about this is, well, the two boxes, essentially this fulcrum is basically pulled towards the heavier boxes. So in some sense, you think of it as kind of like a center of gravity where the boxes pull that fulcrum closer to that. And that's correct. The other way to think about it is think about it as torque. Torque is just the tendency to want to rotate. Now, that is kind of, if you look at this picture over here, you can see where I've got two fulcrums and you've got two masses, one on either side, and the tendency to rotate is essentially represented by those green arrows pointing down. Again, this is gravity forcing that rotation with the bar about the fulcrum. So this is something that Archimedes, absolutely my favorite mathematician ever, he introduced this principle of the lever, which essentially says that weight 1 times distance 1, distance would be distance to the fulcrum, is equal to weight 2 times distance 2. And essentially here weight is of course mass times acceleration. So he kind of was the first person to put some mathematical formulas for this principle. And basically torque is just this tendency to rotate, and we're basically saying, okay, if we have torque is positive, we're going to have counterclockwise rotation, and if torque is negative, we'll have clockwise rotation, so as you can see in the little diagrams here. Okay, and of course, being in balance is when basically all the torque forces are netting towards zero. And of course, whenever you see this word net, you should always remember that's just code for add up to 0, which I'll use the sigma symbol to add. Then I really love the following argument, so I'm just going to go through it real quick. If you start thinking about, all right, what if I have more masses, or in this case, it's still 2, you can essentially look at my equations here, where what if the two masses aren't basically on opposite sides of 0? What if they're just random numbers, x1 and x2, and they still have masses? Again, so this is an issue about coordinate systems that's important to think about. Well, geometrically, you know that the center of mass, which I guess I started using the more precise notation here, where we'll say that x bar is the location where we're going to place the fulcrum. It's going to be somewhere in the middle, so how do we actually find that? Well, the trick is, if distance 1 and distance 2, as you can see in the picture, as long as we keep track of signs to the left or to the right of the center of mass, everything works out quite nicely. Check it out. So you've got x bar minus x1. That is going to be d1. And again, why is it x bar minus x1? Well, if you look at the picture, that should be a positive distance. And on the other side of the picture, x2 minus x bar, because x2 is bigger than x bar, that's going to be a positive distance, d2. Okay, so this is, again, Archimedes' principle of the lever gives us this equation, and basically if you just algebraically solve for x bar, you'll get something interesting, which is just essentially what we call in math a weighted average. So the formula here is that x bar is sum up little tiny masses times the positions that we're having them at. I goes from 1 to n, however many masses we have. And then you divide by the sum of just the masses. Okay, and of course we call the denominator the total mass, and then the numerator, the sum of the mass times the position, or I guess said maybe mass times the distance. This is what's called the moment, and the 0th moment. Okay, so essentially this is the calculation for, if you want, you could actually just pause the video here and look at the equations and just see how the algebra beautifully just generalizes. And let me skip to the 2-dimension situation, where if we've got basically a system of point masses, and if you imagine all the masses are in a plane, and you imagine that cone there, that's our fulcrum, we want to put the center of mass precisely so that everything balances out. And the trick to this is really just to split this up into 2 dimensions and think about them 1 dimension at a time. And the really confusing notation here, you see my little danger curve there, is we say mx is the moment about the x-axis, which is essentially saying we're measuring from the point that we're at. So in this picture here, imagine we're at this point right here. Well, how far is that to the x-axis? Notice that we actually have to measure the yi distance, right? Yi is the distance from the mass to the x-axis. Okay, so basically the moment about x is you take the mass times that distance, which is the yi, and that's where the y and the x, they're kind of flipped, but if you understand that we're measuring to the x-axis, the formula is the formula. Okay, if we do my is the moment about the y-axis, which means measure how far away it is to the y-axis, well, notice that that's where we need the xi. All right, so summing these up in this again, this is what we call the discrete case, where we just got a finite sum of particles with different masses floating around in some sort of plane. But if we work out the algebra is as follows. So the formula for x bar is my over m. But if you actually just focus in on the actual formulas, is you've got the sum of the moment mass I times xi on the numerator, and that's in the x position. If you look at the formula in the y position, right, the y coordinates have the y. So even though these formulas kind of intermediate here are kind of confusing, where again, y bar has a moment about the x bar has a moment about the y. If you actually just work out the details, you're like, okay, the x's and the y's show up in the correct spot. And of course, we've got the total mass in the denominator. Okay, so I've got a bunch of extra insight here that if you're interested, you can pause the video and just kind of read what I wrote there. And, I've also got an example here from the discrete situation that you can kind of take a look at. All right, now I want to show you quickly the way we solve this in Calc 2, because it's quite interesting that we can come up with centers of mass of laminas, but we had a totally different technique for figuring this out. The key was when you break the center of mass, because we only have one variable we can work with, we had to essentially cut this up into thin strips here. So there's a thin strip, and you essentially try to figure out the center of mass of that thin strip. Basically, you can figure out that the the distance from the center of mass of that strip, you can see it's basically at the halfway point. And when you kind of work out the details, you can kind of check this out, right? You do the moment my, that's the distance to the y-axis, and you can see that that is where we have, where is it? Here. That little x, or I guess let me use this color. This is the distance to the y-axis, and then of course we have the mass of the strip, right? So d mass just means the mass of that strip. If we look at mx, that's the distance of the strip to the x-axis. So this is where it gets interesting, right? We actually have to measure from this kind of halfway point, from that halfway point to the x-axis. And what's the halfway point? Well, one way to think about this is it's really the geometric average of the top of that curve and then that bottom curve. So in this notation, let me just read that real quick. Okay, I guess I'm using f for the top, g of x for the bottom. So basically it's just the average of those heights. And yes, you can kind of work out that formula, but it turns out that if you basically do a little bit of algebra, you actually get f squared minus g of x squared. Again, this part of the formula doesn't really make sense geometrically. It's just what you get if you do the algebra and simplifying it, which actually you can see it on the screen and take a photo of this if you'd like. All right, so that's the two-dimensional situation. Now, let's go to Calc 3 version. So it's the same situation where we've got our lamina D, and you see I've got a fulcrum underneath it. That is the center of mass. The question is, how do we find the x and y positions of that point? So we do what we always do in calculus. We start by cutting this up into a little tiny chunk. This little chunk is a little chunk of area. But remember, we're imagining that we've got density now. So instead of dA, we'll think, okay, let's think of this as a little piece of mass. So dm. So what is the moment about the x-axis? Well, keep it in mind that that just means take that little chunk of mass. How far is it to the x-axis? Well, as you can see in our picture, we actually have to measure to the x-axis, it's y. So same situation that we looked at in the discrete case earlier. Okay, so that gives us our formula. Y dm is the moment. And again, this is my favorite way of memorizing these formulas. Moment about the y-axis. This is just as easy as before. And in fact, I think the Calc 3 versions of these formulas are much, much cleaner, where distance to the y-axis, you see that we've got the x, and that's of course because the little tiny chunk of mass, you have to measure a distance of x to the y-axis. Okay, since we're doing a little tiny chunk of mass, this is my favorite formula for my. Of course, little tiny chunk of mass, what do we remember from earlier? Little tiny chunk of mass is just density times a little tiny chunk of area. Okay, so that gives us that our center of mass, which ran out of space, so here they are. Same, or I guess similar equations to earlier, but they're much simplified actually. I want to just highlight that if we do x bar, again, x bar is just common notation for average, and it turns out that these are essentially just continuous averages, but that's kind of more of a statistics point of view. But anyways, so looking at the denominator of each of these, we see that these are just the total mass. Okay, common notation for these is just total mass here. That's our tiny chunks of little bits of mass over the domain that we're integrating. And then of course, what is our total, little chunk of mass is just density times dA. And that's what we've got. What we got in the numerator, well, we've got mass times the distance. And as you look at these formulas here, well, notice that it's an x and a y that show up in the appropriate points. And then, of course, just think of this as a little tiny chunk of mass. All right, that's it. So that is a full derivation of centers of mass. Notice that the formulas are just conceptually way more clean to derive, where, again, and I kind of went through this very quickly, but hopefully you've seen it before, so you kind of remember that it was a little bit involved, right? And again, sometimes that's the case where we were forcing this to look like a one-dimensional integral, so we had to think about it as thin strips. But the generality of thinking about this as little tiny chunks of little area, it actually cleaned up the formulas very nicely. All right, almost done with the theory here. The last thing is I want you to all be aware of what a centroid is. Centroids are, I guess for consistency, center of mass. Definitely think of these formulas as GTQ, centroid GTQs as well. And centroids are essentially the geometric, I like to call it the geometric center of mass. Since essentially if you ignore density completely, if you just, again, since if just pure geometry, if you take the density to just be 1 everywhere, then of course in the formulas above, if that's just 1, it disappears. And in the denominator, instead of having a function density over there, you end up just doing the integral of little tiny chunks of dA, which is just going to simplify geometrically to areas in the denominator. And of course, we've got these formulas where it's x times dA and y times dA in our integrals in the numerator. All right, so I would definitely be prepared to do either centers of mass or centroids. They're essentially equivalent, although centers of mass can be more interesting. So, all right. I do want to just mention that moments of inertia won't be tested. So there might be a few problems on the homework. Definitely you should do them. The key here is that the second moments just correspond to the exponents here. Okay, and this one's I0 is just basically the moment of inertia about the origin, which is essentially, let draw a little picture here. Same idea as centers of mass, where you take a little tiny chunk of mass. Let's pretend we've got a lamina somewhere over here, D. Okay, so the second moments are, again, measuring to the x, to the y, but then you square the distance. Okay, that's mathematically all that is different. Where I don't have time to get into is to actually explain the intuition of why you would even consider the second moments here. And what I wanted to point out is I0 would be the distance to the origin here. And okay, so you see you end up just getting x squared plus y squared. But remember, the distance to the origin is the square root of that. But because we're considering the moment of inertia, where we end up doing square root and then we square it, that ends up disappearing completely. So a couple other comments are, well, these are called second moments, as you can see in the little parentheses over here. So you might be wondering, are there such a thing as third moments, fourth moments, etc.? And there absolutely are. So you'll encounter some of those in much more advanced courses, so I won't say much more about them. Okay, so why don't I pause the video here? Actually, hold on. One more comment and then I'm going to pause it. I've got a couple problems on probability and expected values. This is super interesting stuff. However, it's a little bit too much for us to cover. However, let me just say that it's very useful mathematics, especially if you're going to be a computer science major or a data science major here. It's, the more you look at probabilities and expected values, or I guess the sooner you look at them, the better, since you're going to use those quite a bit. But again, I won't test you on those, and you can consider those homework exercises as optional. All right, so in terms of problems, I would definitely take a look at the ICA, and we'll do an example problem in the next video. All right, thank you.